Okay, welcome everyone. So again, my name is Nathan and I'm joined by my colleague, Charles Holding. We're going to take you through a training today on 9540A testing, 9540A certification, and basically the UL process that we go through for our batteries. A couple orders of business. If you want to ask questions, please use the Q&A to type your questions in. I can't unmute you during the webinar. So if you type questions into the Q&A, Chuck will be able to answer them by messaging. And if he doesn't answer them, don't worry, we will get to them at the end of the training. Another order of business is that we have NABCEP certification today for this course. And so if you're here to get your NABCEP credits, please email us. Our email address will be displayed at the end of the recording. Please do stay through for the entire webinar. We are required to check your participation in order to issue those NABCEP certifications. So please stay for the entire presentation. One other thing to mention to you is that our colleague Daniel Moyer, who is usually scheduled to give this training, is not with us today because Northern California had an earthquake and Daniel lost access to internet. So even though he has access to backup power at his house, the internet company needs to buy some SimpliPhi batteries so that they can provide internet service in the event of an outage like this. So anyway, Daniel's not able to join us, but Chuck and I are going to do our best on this training with you. And so we apologize if we don't have great answers to your questions. We'll do our best, and happy to answer some questions by email if we don't know the answers during the presentation. So as I mentioned, this training is a UL 9540 and 9540A training, and we'll take you through that. We always start with a brief introduction to our company so that you know where we're coming from. SimpliPhi Power has been producing lithium iron phosphate batteries since 2010, so we've got over a dozen years of experience. We've been using cobalt-free chemistry. We use an LFP battery chemistry, and that topic will come up a bit today during this discussion about certifications and fires with batteries and the testings that surround that. We have essentially no risk of thermal runaway, unmitigated thermal runaway with our batteries. As these tests are going to show to you today, we're going to show you the results of these tests as well as talk through the tests themselves and how they are run. So that's the UL 1642, 1973, and then 9540 certification. The UL 9540 is simply a test that informs the 9540 certification, and we'll get into that. Additionally, we have some certifications from the United Nations Department of Transportation, and so we can airship some of our batteries. There is a weight limit to these batteries, and so we're limited to being able to ship a 3.8 kilowatt hour battery, and that's what our certifications are there. So if you need air shipment or being able to transport these batteries on an airplane, we do have some solutions for you, but those are by special order. We also do not use rare earth metals, an example being cobalt in our batteries, and that really avoids kind of some of the downsides to mining that are seen around the world. We are proven, so our batteries have been out in the field for a long time. We've been offering a solid 10-year warranty for a long time. We're deployed in over 45 countries. We have distributors around the world. We've got over 250 megawatt hours installed and backing people like Daniel and people in Northern California up. We've been used by the US Army and Marine Corps for deployments. We've gone through some strenuous testing with the US military back in 2010 and 2011. And so we were involved in helping the military switch from lead acid batteries to safer versions of lithium batteries. Again, I mentioned we have special permission by the FAA to airship our 3.8 kilowatt hour batteries in ABS cases around the world. And we also, as part of our business model, we want to demonstrate a social impact. So I just received word this morning from a a person that is working with a nonprofit in Peru, that we have 6 batteries or 10 batteries safely arrive at their partner in Lima. Those are destined for a school in the mountains of Peru. So if you have projects that require donations, we do have an IDEA program that we donate batteries to every year. And so we're currently accepting applications for that. So keep that in mind if you have a nonprofit or a goodwill type project in mind. Another goal for us with SimpliPhi Power is to keep things simple, right? Built right into our name. We're trying to keep our battery-based solutions as simple as possible for installers to install, right? And what that means is we're trying to provide solutions which require the minimum amount of work on the installer side. And this includes doing our certifications, right? So we are doing the certifications so that it's easier for you to meet the local regulations, etc. Our solutions allow us to store energy for critical backup power. Our solutions allow people to have distributed access to power, right? So individual access to power. You're not having to rely on that electricity company that might go down when a fire comes out or a hurricane comes in, etc. And we believe that distributed access to power, distributed power generation is really the best way to have resiliency and affordable costs with electricity. So there are many different reasons to use our batteries, many different ways, etc. As you can see from this list of distributors around the world, these are places to buy our batteries around the world. And we've got many distributors carrying our products. And we're proven in many different countries that we're especially, of course, being a manufacturer here in Oxnard, we're especially prominent in the Americas. So we won't talk a lot about chemistry. We have specific trainings around battery chemistry, but we will talk a little bit about it in this talk because of the potential for fire, and the potential of batteries for fire is related to the chemistry inside. Batteries are classified as to what makes up the cathode, the positive terminal of the battery, the positive side of the battery. They're also classified as to how they are composed, what the form factor of the individual cells making up the battery is. So on the left side of the screen, you can see we have a number of different chemistries. There's a lithium cobalt oxide, there's NMC batteries, nickel manganese cobalt oxide, which are quite popular batteries because they're low weight, but they also have an increased fire potential, as you'll see in some of the evidence from today's data. There's lithium manganese oxide, and then there's lithium iron phosphate. So this is really not a metal oxide for the cathode, it's an iron phosphate. So iron is a very common metal. We don't have cobalt in our batteries, which makes them a little easier to dispose and recycle as well. And then there's NCA with nickel cobalt aluminum oxide. There are a couple of other variations of battery chemistries which actually involve changing the anode material, the negative terminal of the battery, but we won't get into those in today's talk. Form factor involves the cells, how the cells are made up. And there are 3 principal ways of making battery cells. There's a pouch cell in which you take foils covered with a spray cast cathode and anode material, the positive and negative materials, and then you sandwich that over top of a semi-permeable membrane that only allows the lithium through, and they're filled with an electrolyte gel. Then they're folded on top of each other and sealed inside an aluminum pouch. These are the least durable, but the cheapest types of battery cells to make. So pouch cells are rarely used for battery backup in homes just because they're the least safe type of cell and the shortest lived. The reason they're shorter lived is this batteries swell and contract as they charge and discharge, and without having any support for the battery packs themselves, these batteries end up experiencing the most amount of contraction and expansion, and therefore the least lifetime because of the degradation associated with that. There are also prismatic cells on the bottom. So those prismatic cells are generally large battery cells. They're made in a similar way, but they are encased inside of a rigid plastic casing, which provides some structural support to the batteries. You can typically get prismatic cells in very large capacities, so they come in large sizes. They're a little bit cheaper than cylindrical cells, simply because of the manufacturing process. You could produce big cells. They're a little bit shorter lived than cylindrical cells, and they have a little bit more problem with buildup of temperature, simply because the cells are larger and it's harder to get that heat out of those cells. And then there are cylindrical cells, and these are, you're familiar with, just in the form of AA batteries, AAA batteries, D cell batteries, C cell batteries, etc. Lithium batteries can be made in a similar way. It includes a steel casing with those layers of material wound up inside the cell, and tabs at the top to make those electrical connections. These fills, all of these cells are filled with an electrolyte solution, which is what allows the lithium to be mobile inside the batteries, and is what is related to the potential for lithium batteries to catch on fire. So a lot of people think, oh, it's the lithium inside there, inside the cells, which is catching on fire, because they know that solid lithium, when exposed to water, can rapidly burst into flames. But it's actually the electrolyte, which can become gaseous at high temperatures. All of these cells contain electrolyte. Pouch cells are very easy to puncture, right? You can imagine a nail or just a sharp edge going through a pouch cell easily. Prismatic cells and cylindrical cells are less easy to puncture. However, they all have to be vented. So to prevent any risk of explosion, both the cylindrical cells and the prismatic cells have vents on the top of them that can release gas if it starts to build up at high temperatures inside the cells. So give you an idea of what can happen, right? Batteries have gotten a bad rap. Lithium batteries in particular have gotten a bad rap for the potential to cause fires. Can it happen? Yes, it can happen. What does it depend upon, right? Well, it depends on environmental considerations, right? It depends on what temperature the room that the batteries are housed in. It very much depends on LFP versus other oxide, metal oxide. So the chemistry of the battery matters a lot in terms of whether or not a battery will burst into flames, or it can even burst into flames. Some YouTube searches on LFP puncture tests versus NMC or NCA puncture tests will show you a big difference. And so there's some, I know Will Prowse has some videos. Chuck, do you know Will Prowse's handle on YouTube?
I can look it up, but this was the real eye-opener for me when I first watched one of these puncture test videos where the LFP just kind of fizzles. You know, you can see a little bit of release, and then you go through an NMC battery and it ignites, it explodes. It's very dramatic. So I'll have that handle for the Q&A, which is populating. So thanks everybody for your questions.
Sure, yeah, and so he does a side-by-side puncture test of an LFP battery as well as an NMC battery. And actually, I believe that the battery he had ordered was labeled. It was coming from Asia, and it was labeled the solid-state battery. And his puncture test proved that that definitely was not the case. So you also have to be careful about who you're trusting to buy your batteries from, because the labels might not match, right? So this is the reason for having standardization and testing and trusting different companies. So what you're looking at in the top left corner is an exact example of what I'm telling you. So a puncture test is where you actually take something that's metal conducting and you puncture a cell and you look at what happens. So if you puncture a cell, especially with a sharp metal object, it will connect the positive and negative sides of the battery, essentially shorting the battery out, releasing that built up energy inside the cell rather quickly. As Chuck mentioned, LFP batteries, you will see some smoke come out of them. But what you don't normally see is what you see with the NCA battery there. It's a rapid release of sparks and flames coming out of that cell. And that's just because the chemistry is a little bit different. That presence of cobalt releases a lot more energy, which can vaporize the electrolyte faster. So there are some examples of fires here shown with NMC batteries. There's a large example of, there's a power plant with Tesla cells south of me here in California, which has caught on fire a couple of times now. So it's an important consideration, right? There's LG Chem cells that are shown there, that's NMC, and there's a battery fire there, it looks like in Korea. And so LG Chem has recalled some of their batteries and is showing you there that in 2020. And then what you're seeing in the bottom right-hand corner is an example of what I was talking about, the Tesla battery fire that lasted for 4 days. So we're not showing you these to give other companies bad raps. It's certainly, there's the potential for fires with batteries, and we think the benefits of batteries certainly outweigh these, but the type of chemistry you use increases or decreases that risk of fire. So what I'm going to talk about today, this training is about UL certifications. And I know in particular, installers and battery dealers are most interested in what the rules are and how they can follow the guidelines. So I'm going to start off talking about the UL certifications. So UL certifications include battery cell level certifications, and that's 1642. So on the left side of your screen, we're talking about taking an individual battery cell and exposing it to all sorts of rough conditions. We're going to shock a battery. So example of this might be a battery pack falling off of a wall, right? So you want to make sure if you take an individual cell and you shock it, you vibrate it, you drop it, potentially you even heat it, right? So maybe accidentally you place your batteries too close to a heating source, or maybe you have a small fire that breaks out in your garage for some other reason. You're welding and something catches on fire, right? And that's near the batteries. What's going to happen to those cells? So we expose them to temperature cycling, heating, cooling, low pressure. You could simulate that, right? Altitude simulation, or you've got your batteries flying in transport, right? You're taking your power tools with you on a project across the country. You check them, right? So we want to make sure that batteries are capable of going through all of these exposures. So you crush a battery. Unfortunately, you back into a battery pack and it crushes one of the cells. What's going to happen? So individual battery cells are exposed to all of these conditions like forced discharge, humidity, etc., to make sure that when they're in the field as part of battery packs, that they're not going to burst into flames or short or off gas. And so if the cells pass the 1642 certification, they can be used to produce battery modules. So typical battery modules have hundreds of individual cells in them to create the total battery pack, right? So a module here is what you normally think of as a battery, made up of many cells, right? Typically around 400 or so cells, or 400 to even 1,000 cells in large batteries. So the 1973 certification is the certification for the whole battery itself, the module, the BMS. So BMS stands for Battery Management System. So once you combine all those cells and you produce a battery, right, that battery contains a BMS. The BMS has several safety features in it, such as short circuit protection, etc. And this is put through also a wide range of abuse: electrical abuse, shorted out, thermal abuse, heated up. And the component battery cells cannot experience a fire or an explosion. If they do, you don't get that certification. And so our batteries are exposed to all of these things. The battery management system is there to protect for extreme circumstances, okay? Then there's a UL 9540A test. So I want to emphasize all the others, the UL 1642, UL 1973, and UL 9540, these are certifications. 9540A is just a test. The test is designed to look at batteries, purposefully create a fire in the battery, see how the battery responds, in order to know what requirements will be surrounding the 9540 certification. So what we do in the 9540A is we take cells and we expose them to thermal runaway. We expose them, we basically cause the cells to catch on fire in certain configurations, monitor the conditions with tons of thermocouples. So thermocouples are digital thermometers, right, placed in different locations. And that'll allow us what minimal spacing we can have between batteries, etc., when we go to do the UL 9540 certification, okay? So the UL 9540 certification is a system level certification. What I mean there is if you have a battery backup system, an ESS system, That system will include an inverter, will include a charge controller, will include batteries, possibly batteries inside battery casings, etc. Right? And so we take our systems through a system level certification, and anything matching that certification in the future will be able to be installed with 9540 certification. Not every jurisdiction is requiring 9540, only some jurisdictions are. So what I'm talking about here are the certification processes, and as more and more states adopt these certifications, it will be required in more places. So this UL certification, the 9540, didn't start until 2017. And I'll get into it and also talk about our systems that have gone through this 9540 certification. We're going to start off with the test. So UL 9540, a fire safety test. We're going to force these batteries to catch on fire, and we're going to monitor the conditions to make sure that they're safe. Okay, so as I mentioned, this UL 9540A test method was developed in 2017. It's gone through a number of iterations. I think the most recent change was in 2019. We're currently in the 4th edition, so UL is in the 4th edition. UL has methodology for conducting battery, cell, module, and unit fire tests, right? And that's what I was talking to you about in the previous slide. What we're going to do is force thermal runaway. You can imagine a real condition where a battery system is placed where thermal runaway is forced. For instance, house catches on fire for some other reason, right? And there's battery storage inside the house. There's a battery ESS system. So this could replicate, you know, the conditions of the 9540 test, and that's what we're going to get into. The data from this test is what's going to establish the risk profile of the batteries. It's going to tell us what conditions the batteries should be placed in to meet the safety expectations and demands of the 9540 certification. Okay, so as I mentioned, I'm not going to take you through all of this, and I apologize if the text is too slow, but basically the 9540 test is a series of progressively larger tests. So we start off at the cell design, we look at the cell, we look at the behavior of the cell, we put the cell into thermal runaway, make sure it doesn't explode, etc. If the cell performs properly, if the cell doesn't provide any indications that it will not be safe, no further testing is required at the cell level. The cell then can be used, right, to produce modules that can be certified with 9540, or sorry, 1973. And the module also goes through all of these similar testing. We're going to evaluate the module design. We're going to make sure that the BMS is safe. We're going to look at the heat release rate if we heat up the battery module itself. We're going to look at an external flaming, and possibly if you have a battery that can explode, the risk of exposure as well. That's deflagration of the battery. And so if all of these tests on the module are okay, no further testing is required, and we can proceed to the next stage of the test. So this is a very involved, fairly expensive test to run, and there's a lot of data that comes out of it. So once the module passes, once the battery itself passes, it can be included in an ESS system, right? And a battery ESS system design then gets looked at. We look at the heat release rate. We look at the generation of gases during it. We look at the potential for deflagration, which is explosion. We look at possibility of flying debris in the event of an explosion. They're testing to make sure that surface temperatures don't get too hot on the battery walls, or even the container walls, or the potential for reignition after a fire might have even gone out. So if all of this goes through, we proceed to the next level, right? And this is the installation level test, where we're looking at all the protection equipment. We're looking at a full installation, and we'll go through each of those steps in detail. So why are we doing this, right? Safety matters, right? And especially there are some very strict regulations for batteries in high-rise buildings, right? So fire departments like the New York City Fire Department have very strict regulations of batteries, because keep in mind, you know, a fire on the 42nd floor of a high-rise building has a huge potential for destruction compared to maybe a garage fire or smaller fires. And so there's a real need for safety, and we are very aware of that. SimpliPhi power batteries might be the most tested batteries in operation in the US. We go through all of these safety testing. Safety is a very important part of our business model, and it's very important to us that our customers have safe options to back up power with. So again, that is one of the principal reasons we use LFP batteries. Longer lifetimes, but also a much greater safety surrounding LFP batteries, lithium ferrophosphate batteries. NMC batteries are typically the batteries you see in fires. If you see a car accident where battery cells have been punctured and shorted and it results in a large fire that's very hard to put out because you have this continuous production of fuel with a car, those are typically NMC batteries. I do want to point out that battery-based cars are not the only thing that can catch on fire. There are many times more battery fires with gasoline and diesel powered cars than there are with battery-based cars. So I don't want to give batteries a bad name just because we're talking about the potential for fire. They're actually less likely to catch on fire than gas and diesel powered vehicles. So these certifications, the adoption rates are kind of varying. California, New York, and Massachusetts are kind of leading the way with UL 9540. I do know that Arizona jurisdictions in Arizona are requiring 9540 as well. And again, the reasons for this are there on the right. We want to have safe batteries that offer consumer safety, but we also want to do these tests so that we can have informed decision-making by installers and homeowners. There's also the need for resiliency and energy security, right? If you have batteries that are catching on fire, that's not providing more energy security. And then, of course, if you reduce fires, if you reduce problems with battery systems, you're overall going to save customers and businesses money, right? We don't want fires. Okay, so let's get into why the UL certification matters. Again, it's often mandated, and so many times installers are simply having to follow local rules and guidelines. The UL 9540 test method informs things like ventilation, right? So batteries can give off harmful gases if they do catch fire. We want to make sure that we monitor those and make sure that we're installing things in a safe way. Certain jurisdictions have off-gas system monitors built into them. So I know that our solutions in New York City are required to have off-gassing monitors. If you are found to produce lots of gases, you might also need special ventilation equipment. And so again, the test informs the strategies and tactics that we may need to incorporate to eliminate these risks, as well as safety characteristics. So providing this kind of bar, this standard of safety surrounding your batteries, so that you know what kind of safety that the batteries have. And then it encourages safety within the industry based on having these reports published. We publish our 9540A battery tests. We're one of the few companies that does that. We encourage other companies to publish their safety tests so consumers can make very informed decisions. Here's what happens in this test. What we're going to do is we're going to take a battery module. We're going to place thermal wraps on individual battery cells within the whole module. And so what you can see there is a placement of thermal wraps. So we're going to take 7 cells, we're going to wrap them with heaters, and we're going to heat up an individual battery cell. And the goal of the test is actually to heat that battery cell up so much that it off-gasses. So again, as I was telling you in the beginning, all of these battery cells are injected with an electrolyte. It's an organic liquid that allows the lithium to be mobile. That organic electrolyte can give off flammable gases. And so the goal with this test is to actually produce an individual cell to off-gas. Not only that, it's to produce enough heat to get all the cells around it to also off-gas. So this is the process of the test. We're going to artificially heat the cell up till it off gases, and we're going to look at what happens. And there are both heater wires going into that battery module in the bottom right, as well as thermocouples to measure the temperature at different locations within the battery and collect data on how the battery performs. Basically, test results concluded that our LFP battery cells and modules did not create unlimited thermal runaway. So by getting multiple battery cells to off gas, catch fire, and produce additional heat, we didn't end up with a chain reaction which made all the other battery cells around them do the same, right? And so this certification, this test procedure is what allowed us to kind of move forward in the testing process. We're going to go on to look at the data from this. So I want to point out that what you see on that graph on the left side is the temperature of individual cells, right? And so we're specifically heating these cells up, and we're monitoring temperature at different locations. So there's, I think, 8 different cells that are being monitored here, as well as different locations inside the battery module. And what you can see if you follow this graph up is it's getting hotter and hotter and hotter inside the battery cells themselves. You see some kind of rough data coming in. That has to do with the off-gassing. So around 200 degrees Celsius, you can see some off-gassing that's occurring here. That off-gassing is actually a rapid reduction in pressure, and so it's accompanied by a slight decrease in temperature. So that's the kind of noise that you're seeing there. And then those heaters continue to heat the cells up, and all of a sudden, around 35 minutes in, you see a rapid spike in temperature. Okay, that rapid spike in temperature is occurring when the flammable gas that's coming off the cells can actually burst into fire, right? And that releases more heat, more temperature. However, what you can see is with this particular battery module, it didn't just continue to go up in flames. The rest of the cells, the rest of the 300 or so cells within that module did not catch fire, and you can see the temperature of these battery cells gradually decline after the off-gassing event. Top right-hand corner, what we're doing is we're measuring the production of different gases. So as you're probably well aware, when combustion does happen, carbon dioxide is produced, water vapor is produced, carbon monoxide is produced as well. And what we're measuring there, right, is the production of those gases to make sure that they're not occurring at a dangerous level. And what you're looking at the very bottom of the graph is a minimal amount of production. So we don't have some rapid production of CO2 and CO that could lead to very dangerous circumstances. On the bottom, we're looking at smoke release rate, right? So smoke is also a hazard for respiratory, for breathing, right? And for people with respiratory conditions. So we want to make sure that we don't produce too much smoke as well. And so we're looking at a smoke release rate. Again, this is really at the bottom of the scale in terms of what we're looking for with the UL certifications. The unit level test is where we take a bunch of batteries, a bunch of battery modules, and we put them in close proximity, how they might be end up being placed in the field. So what you can see here, this is a BOSS 12 enclosure being tested. We're testing a 136.8 kilowatt hour battery system, which includes 3 of these battery cabinets side by side in the testing setup. So again, we're going to take an individual battery, we're going to force it into thermal runaway, and we're going to see how the other batteries around it respond. There are 93 thermocouples in this setup. We're measuring temperature at all sorts of different places. We're measuring temperature inside batteries, on the outsides of batteries. We're measuring temperature on the casings. We're measuring temperature on the surrounding casings. So we're measuring temperature in 93 different locations. And these thermal measurements are going to be reported and established as we watch the forced heat rise inside the battery itself. So we're going to heat up battery number 7, or I think that's maybe battery number 8 there in the bottom, which is circled. And we're going to look at how the temperature of the surrounding batteries respond once we force that individual battery into thermal runaway. Here's what the testing setup looks like. We have we have the spacing dimensions. We have only 12 inches between those individual battery cabinets. Those cabinets are then to meet the NFP code are 36 inches in front. So that's the spacing, as close as we could get. And we've got, again, like I said, 136.8 kilowatt hours of battery that's there. They are surrounded by a 3/4 inch plywood wall, as well as there's the room that they're being tested in is 12 feet wide. And I think in this particular setup, we're looking at an 8-foot tall ceiling as well. And the presence of these walls is to actually, replicate a room, because having those walls there, they keep the heat in and keep these units at higher temperatures, right? Which was similar to the installation they might be in at a site. Okay, so yes, it was battery number 8. We're looking at battery number 8, and we're going to heat this up. We're going to measure the temperature on the casings of all the batteries around it as well. And so we've got many different thermocouples there, 24 different thermocouples, looking at just surface temperatures of the other batteries as we go through the test. Then we're going to measure temperature inside the battery as well. And so we're looking at what we're showing here is all of the different thermocouples that are either inside near the heaters. So again, we're wrapping individual cells in heaters to try to get them to catch fire. And we're going to monitor those temperatures of the individual cells, as well as surrounding cells, as well as the case of the battery that we're forcing into thermal runaway. Then we're looking at the casing here. Now, this is the casing of the battery container, the BOSS 12 cabinet. We're looking at that the metal walls there, and have thermocouples in many different places around the walls to look at what temperature it might get into, to see if it might be an ignition hazard for other things possibly at that location. Okay, so what we're doing here is we're going to force this battery cell into thermal runaway. We're going to look at the temperature that results, and we're going to look at the venting that occurs. And so once you get the cell temperatures hot enough, you're going to have venting. That venting can then produce thermal runaway, and we're going to see if it's mitigated, see if it stops on its own. Some important things to note here. As this test was being run, there was no fire or explosion detected outside of the batteries, right? So there was no big fire, even though we're trying to force a fire to happen. There was no module to module propagation. That means that even though battery 8, we forced it to off gas, we forced it to go through a thermal runaway by actually placing heaters inside it. Batteries number 9 and number 7 right next to it did not go into thermal runaway themselves, right? Not only that, but the highest temperature of the adjacent batteries outside of the battery that was forced to go through an off-gassing event was only 60 degrees Celsius. And after we concluded the test and turned the heaters off, the temperature rapidly dropped after the test was concluded. So again, this is really showing you that there's some safety here. This is not a certification, just a test, but it's showing you that it was really kind of an unremarkable test. These tests it's kind of fun to watch fires, right? And so these tests can be exciting to watch. And ours are really fairly boring. We do share the data, we do share the pictures, the videos with you, and there's not much to it, right? You can see a little bit of smoke come out, but you're not really seeing something bursting into flames like you do see with NMC battery tests. So the back walls of the enclosures of the BOSS 12 cabinet shows a 5-degree temperature rise. The ceiling height was reduced to 8 feet, like I mentioned, to demonstrate a more constrained space, such as typical in homes, typically 8-foot ceilings in homes. We had 0 hydrocarbon gas released and no flames observed. Remember, outside the cabinet, we're not seeing any problems, really. Now, that doesn't mean that there's no smoke released. Yes, there was some smoke released. There was some venting occurred. We're forcing it to occur. It has to occur. And then I can't speak a lot about the data on the right. It looks like looking at the rear wall and the side walls and the soffit temperatures. I do believe that this is the walls of the test facility. So we're looking at the temperature of those plywood walls around the battery banks. And you can see that they really didn't heat up much there. They were only going slightly above room temperature. So not a lot of heating occurred in the room where the batteries were installed. And they were monitored in many different locations. So even though we had, we're noting the smoke release time there, we did see a slight rise in the temperature of the walls, but we're only looking slightly above room temperature. So what this data is showing you is kind of, we don't have potentially hazardous hydrocarbons being released into the environment. That's what would occur if you had a rapid off-gassing event where you have the production of hydrocarbons, which are flammable gases, but you don't have ignition. And so not having those present means that there's no health risk associated with hydrocarbons. And so none of these tests showed any flames observed or any kind of problems. And so this, as I said, is fairly unremarkable. Again, there was smoke released, but it was well within the limits of UL certification. This is the start of the recording. So we're looking at recording of our testing process. We're looking at, so that the unit is contained in a plastic bag in the back corner there. And I believe that plastic bag is there to monitor off-gassing. But unfortunately, I'm not sure. As I said, normally I was not the one scheduled to give this training, so I'm less knowledgeable about it than Daniel, but I believe that's what we're doing there, is just trying to capture the gas, and we probably have a gas monitor that's there collecting that data. The wires that are running in there, those wires are data wires to bring back the information from the thermocouples, as well as to provide the heating source to force the battery into a fire. On the left side, the reason I said our tests are kind of boring, on the right side, you can see that well into our tests, you're not really seeing much happening from our batteries on the right. But if you look at the test on the left, this is what happens with an NMC battery. Not all, but a competitor's battery is bursting into flames there. Remember, it didn't do it spontaneously. The purpose of the test is to make it catch on fire. But look at the difference, right? You can see the hazards associated with some battery solutions compared to others. And so what I'm saying here is that, you can choose batteries that have reduced risk, and that offers, the lower probability of this kind of happening to you or your customers in the future.
Yeah, Nathan, I think it's really worth noting that some of these tests are very dramatic to watch and can be prolonged. It could be a 3-hour plus fire where they continue to record. They may be using sprinkler systems to put the fire out and it's not going out. Our test is unremarkable because we don't have that runaway. We don't have, as you can see on the left, you can actually see sparks shooting, so you have that deflagration radius that now has to be a consideration for that product because, those sparks could be igniting further fire at that radius.
Yeah, thank you, Chuck. And yeah, so there is the potential for creating other fires. There's something called a deflagration. So deflagration is explosion, right? And one of the things about battery fires that makes them particularly hard to put out is you can have a continuous source of flame, right? As cell after cell off gases. And remember, all these cells have to have vents on them. They have to be able to off gas so that they don't explode. But keep in mind that you get these vents very hot and they can fail. So what Chuck was saying, you see sparks flying out. Battery cells can have the vent fail, have pressure build up, and then be an explosion hazard in addition to an off-gassing and fire hazard. So the fires can be hard to put out because you have a continuous production of fuel, right? As well as there can be an explosion hazard as well. And so some batteries need what's called a deflagration radius to protect them. So we conclude the 9548 test. We get all of this data from the test, and then we can move towards UL 9540 certification, which is a system level certification, which includes how you connect the batteries, how you use combiner boxes, what inverter you've chosen, what charge controller you're choosing. And so it's specific to our 9540 certifications. Keep in mind that if we have, so these are different certifications that we have. from our testing. And what you can see there is some memos from the Fire Department of New York giving us permission to use our battery backup systems in New York, one of the most stringent jurisdictions. And so keep in mind, though, if there's a 9540 certification surrounding a particular inverter, a particular battery system, you can't just swap out one of those components and have the certification be valid, right? So we have 9540 certifications of our batteries within these access cabinets. So an access cabinet has an inverter inside of it. We have 9540 certification on our batteries with solar inverters, and I think it's with Schneider, and I'm embarrassed that I don't know that. So it's so I'll have to come back to that at the end. I'll have Chuck look that up. But we have 9540 certifications on those access cabinets. We have them on our enclosures paired with those inverters. Those inverters do not need to be inside the cabinets. So we have those certifications for you. And you can present those to your jurisdictions, your AHJs, and basically meet the building inspector requirements. So at SimpliPhi, we believe in accelerating the energy transition, right, towards batteries. Electrification is happening. Electrification of cars, I think, is a very good thing, and it is happening. And also electrification of homes, right? More and more things are being powered by batteries. And one of the beautiful things about batteries is being able to have that battery backup so that when the grid goes down, like for the case of our colleague Daniel, who's absent today, right? Because the internet company is not able to provide service, having your own access to power is important. And we believe in accelerating that transition. We also believe in reimagining the power grid, right? Having distributed sources of power, eventually we'll have kind of on-demand systems where the power company can say, hey, I need you to discharge some of your batteries to the grid because I'm producing at capacity and the demand is high. And so the grid will be changing, right? And we're hoping to build a more resilient energy future by delivering battery solutions, as well as saving our customers money. Right? I have solar panels, but I don't have them up on my roof yet. And I know from my bills that come in every month, right, that I'm wasting energy by not generating my own energy for free using solar. So we have some deployments just showing you here. These are some deployments of our battery-based solutions in New York City. We've got some on schools, on New York City public libraries. We're one of 3 battery companies that's able to provide battery backup solutions with appropriate certifications from the Fire Department of New York, meeting those building requirements. And so the challenge here was to optimize the solar production, right? This is for a school, and the solution here is to retrofit a segment of the PV to be AC coupled. And this provides stability for the local community, as well as storing potential with battery backup. And again, trying to provide some access to energy for low-income households as well. And so I want to thank you for attending. Our CEO, Catherine Vonberg, has given this talk before. Daniel's given it as well, and we'll be doing it in the near future at the NABCEP conference. So if you attend, you will find Chuck, Daniel, and I presenting talks there. So I'm going to move into questions and answers. As I warned you at the beginning, I may not be able to answer all of them unless
no. You've got the questions. A couple things you asked me to follow up on. Originally, we talked about the puncture test. There's a great YouTube personality, Will Prowse. His tag is just Will Prowse. It's WILLPROWSE. So you can check out his video. He's really looking at all kinds of off-grid and battery-based systems and doing reviews on them.
Yes, and he's done some excellent puncture tests that I encourage you to check out, just showing you the difference. And as I said, showing you mislabeled batteries, right? Solid state batteries don't have electrolyte. They shouldn't go through an off-gassing event. And so he's done some puncture tests on batteries that he's purchased, low cost batteries that say they're one thing, punctures them, and obviously there's something different. So I encourage you to Google some of those as well.
You also asked about the Schneider access system, and according to our documentation, whereas the Solarc access system is 9540, we are not advertising it on the Schneider side, so I think it's safe to say that we haven't gone through that testing process. We've just done it with the Solarc 12K, and to Nathan's earlier point, it's a question we get a lot. Those tests are specific to the equipment that they're tested on, so you can't swap in somebody else's battery, you can't swap in another inverter. Those tests need to be run again with that equipment to get that certification.
Thanks, Chuck. And I'm going to run through these questions. So Jody, you asked, do you have LFB onboard US Navy ships currently? I think the answer is probably yes, but I am not sure. So I'm going to have to look that one up and get back to you on that. You can submit a question by email to the email address is training@SimpliPhi, spelled with PHI, power.com. For all of those of you who are wanting to get the NABCEP certification for today's course, again, training@SimpliPhiPower.com. I'm sorry, I don't have that link up here. I meant to include it on the last slide here. So I think, but I'm not sure what current batteries are with the military. As I said, we have a long history and some portion of our origin story is associated with our connection to the military and those tests. You also asked, we are working on a portable battery bank with Donar Mobile, powered DoD, and we need non-flammable, energy-dense battery. So again, reach out to us, training@SimpliPhiPower.com. Kurt asks, is the electrolyte organic or inorganic, aqueous or non-aqueous? So it's a non-aqueous, it's organic, it's PCl6, I believe. And yeah, so you don't want to have water, with lithium, so it's non-aqueous and it is organic. There are options for having people are working on solid state electrolyte, which would be a non-liquid, but still that allows lithium to migrate through it, but does not allow electrons through. And that's one of the challenges of creating batteries is you want to have a pathway that ions can move, but you want the electrons to flow through your circuits so that they can re-meet on the other side of the battery. So it's organic and it's non-aqueous. Joe asks, I have a 40 kilowatt, I have a 40 kilowatt hour system of LFP charging at 100 amps per, so 25 amps per cell. I think you might need battery unless you have larger prismatic cells, and discharging at 150 plus amps. Never seems to have any impact on the battery temperature. It just sits there at ambient temperature. Am I just lucky, or is this typical or normal for charge/discharge currents for all LFP ESS systems? Okay, so to answer you, Joe, typically you do not see a whole lot of heating. So the heating depends on the current, right? It depends on the square of the current, actually, and it depends on the internal resistance of the battery. So you have a 40 kilowatt hour system, right? And typically we'd like to see that charge and discharge at a max rate of C/2. A max rate of C/2 for you would be 20 kilowatts of power. But you're only doing 100 amps, and I'm assuming, I don't know because you haven't said it, but I'm assuming 48 volts. 100 amps at 48 volts is only 5,000 watts. So you're really charging here at a rate of C/5, right? And you will not see a large change in temperature of the battery. The battery has what's called a heat capacity. And so as you're generating heat inside the battery, it will slowly increase its temperature, right? And as you stop using the battery, it would slowly decrease. But if you're continuously charging and discharging, eventually you have this balance of heat that's generated inside the battery, leaving the battery, right? And when you have a balance of heat inside the battery compared to that leaving the battery, that's when your temperature is stable. So the battery has to get a little bit above room temperature in order to get rid of that heat that it's generating. But yeah, that seems fairly normal to me. They do not change temperature that much. It's when you discharge at a rate of C, so we can discharge a single individual 3.8 kilowatt hour battery at 100 amps. but only for 10 minutes. And you will see a small temperature rise. And the reason we stop it after 10 minutes is that temperature rise gets to a higher point, which could cause more problems inside the battery. But yes, compared to lead acid batteries, lithium iron phosphate batteries, and even compared to other battery temperatures, just don't change temperature that much. They're just a lot better at producing the energy without producing the heat. Thomas Merrill writes, what are, sorry, that one just moved for me. What are others using to meet level rapid shutdown requirements?
This one, Nathan, I think, module level rapid shutdown is a solar question, and we are very, very often a solar battery. But what you're talking about is keeping the array safe for a firefighter who may need to vent that roof for in the event of a fire. And so they don't want to be cutting into a high voltage DC array, proposing danger to that fire person. So a lot of solutions out there on the market. Our new ESS has AP Smart integrated rapid shutdown transmitter. There are other standalone rapid shutdown transmitters, DC to DC optimizers, microinverters. It really probably in its own right warrants its own hour-long presentation. But that is specifically a solar and a rooftop solar question.
I think so. And if you did mean module levels shut down by battery module, then all of our individual batteries also have breakers on them. And we do recommend a DC disconnect between the batteries and the inverter, although the breakers do count as a disconnect as well. But I think Chuck's probably right. I think you were asking probably about the rooftop, but if not, feel free to clarify. Jody said, please email me a certificate. Jody, I can't do that until you give me your email. So if you send me an email first, I will reply with your NABCEP certificate. So training@simpliphipower.com. And then somebody asks, an anonymous attendee asks, is 9540 and 9540A something specific to lithium-ion batteries, or does it apply to carbon lead batteries and carbon nickel batteries? That is a good question, and unfortunately, I don't know the answer. So if you would like to send an email to training@simpliphipower.com, I can get that answer for you. I think it's just for lithium, but I actually don't know that. It might be for all ESS systems. Chuck, do you know?
I'm going to fall back on that UL 1741, which isn't one we've talked about a lot, as the inverter certification. And I'm going to believe that these are going to apply to all ESS systems, regardless of chemistry, because that inverter certification, which is part of UL 9540, you got to have the 1973 on the battery and the 1741 on the inverter to kind of get to that 9540. So of course that inverter is not lithium ion based. So I'm gonna fall back to what Nathan was saying. And I think this is all ESS are going to face a similar roadblock of providing a 9540 certification in some AHJs. But of course, that would be a good question for your AHJ to say, hey, I'm proposing a carbon nickel battery system. Do I need this certification? And they would be the ones to provide you that answer.
Good question, and thanks. We enjoy getting stumped, and so feel free to email us as well, and we can dig in with you if you like. Let's see, it says, Thomas Merrill says, no solar, as all the inverters you use are string inverters. So I'm not sure what you're asking there, Thomas, but you clarified. We've had issues with LFP batteries in temperatures below 42 degrees Fahrenheit. They will discharge, but they have issues discharging. What is your low operating temperature? So Thomas, good questions, great question. So I'll clarify two things. So one, our operating temperature on our non-communicating batteries is 32 Fahrenheit. Our batteries with advanced BMS units that monitor temperature and have communications can actually discharge at lower temperatures all the way down to, I think it's negative 20 Fahrenheit, but they rapidly slow down the rate of discharging. So what happens is that why the lithium batteries have trouble charging and discharging at low temperatures, so we can discharge at lower temperatures than charging. But what ends up on the charging side, and Chuck's going to bring up the exact numbers for us, but what ends up happening on the charging side is that the rate at which the lithium moves into the anode material, which is graphite, slows down, and therefore we have to slow down the charging. So we can charge down to 32 Fahrenheit, and then we can charge slowly at temperatures below that. We can discharge at even lower temperatures. So Chuck will give you the exact numbers here in just a second.
I'm sorry, I'm not pulling it up. I want to say it's -2, not -20 Fahrenheit that the SimpliPhi can go down to at that reduced rate.
Okay.
I'll continue to look here.
And those specs are in the spec sheets for all of our batteries, as well as the manuals. So I encourage you to just look at them. But discharge rates, we can go well below 32 Fahrenheit. In terms of discharging, there's not as much problem on the discharging side. And typically charging happens during the day when temperatures are warmer anyway. But if you have cold weather solutions that you need, we can offer those solutions. We have heating pads that can integrate into our batteries, into the BMS system, and charge and discharge based on the internal temperatures of the battery. So we have heaters that we can offer as well. So I think that concludes all of the questions. Kurt had wrote all ESS batteries, so I think he was answering our question there. Does it apply to the lead acid? And I think the answer is yes from Kurt. We're happy to look into more things. Again, one last time, thank you for attending. Please email us at training@simpliphipower.com if you have any more questions or if you need your NABCEP certification. So thank you. Have a good day, everyone.